This is section 10.1, solving systems of linear equations using matrices. So we're going to be solving systems using matrices. Let's first begin by writing an augmented matrix. So a matrix is a rectangular array of numbers. And you can see here to the right, both of these are examples of a matrix. And a matrix can be used to represent a system of linear equations written in standard form. To do so, we extract the coefficients of each term in the equation, and that's how we form the augmented matrix. A bar within the augmented matrix separates the coefficient of the variable terms in the equations from the constant terms. And let's go ahead and see what we mean by this. Looking in number 1, we're going to write the augmented matrix. So as you can see, we do not have in this second equation of the system a term of x. So we're just going to use 0x there, okay? So the augmented matrix, we'll go ahead and use this symbol. We're going to write 3, -1, and we're going to draw a vertical line and write 10. And then a 0, 5, and a 12. And that is the augmented matrix for the system in number 1. Let's go ahead and do the same thing for number 2. Now we have a little bit of work to do first. We could go off to the right and see what we have. So we have 2x plus 3x plus 3y. Maybe I'll go below and then I'll do the matrix to the right. So we have 2x plus 3x plus 3y equals 1. And then we have 6x minus 6y equals 14. Let's go ahead and combine our like terms here. And we have 5x plus 3y equals 1. And 6x minus 6y equals 14. So our augmented matrix will be 5, 3, and a 1, 6, -6, and 14. Looking at number 3, we have x plus 0y plus z equals -1. I think I might write below this one again. So we have x plus 0y plus z equals -1. 2x plus y plus 0z equals 5. And we have 0x minus y plus z equals 3. So now for this matrix, we will have a 1, 0, 1, and a -1. 2, 1, 0, and 5. 0, -1, 1, and 3. Okay, now we are going to work the other way. We are going to be given an augmented matrix and we're going to write the system of equations. And as you can see here, we just have x is equal to -3. Remember, this is where equals is, where that vertical line is. And we have y equals 0.05 and z is equal to 12. Looking at number 5, we have -8x plus 7y equals 113. And here we have 2x equals 1/3. Okay, Now let's begin with some row operations. So what can we do with these rows in our matrices? Well, what we are allowed to do, so these row operations are operations that are allowed and they don't change the matrix itself. They don't change the solutions of the system. So all of these are operations that are allowed. So what are we allowed to do? At any time, you can interchange two rows. So let's look at this. If we're given this augmented matrix on the left, if we wanted to interchange both rows, we would write 1, -2, and a 10, and 3, 2, and a -5. So we were able to do that, and the solution of that system will be unchanged. We're also allowed to multiply a row by a non-constant 0. So here, what we're going to do is we're going to multiply row 1 by 3, and we're going to replace row 1 with that. So if we're going to multiply row 1 by 3, we have 9, 6, and a -15. And then we have not touched row 2. And the last operation we're going to look at is we're going to add a multiple of one row to another row. Okay? So here we were allowed to multiply a row by a constant and we replaced that row with it. Now we're going to find a multiple of another row and we're going to replace a row with this. So we're in this example, we're going to take twice row 1, add that to row 2, and replace row 2 with that. Okay, so we're going to add a multiple of row 1 to row 2. So let's multiply 2 times row 1, and we will have 6, 4, and a -10. So we're going to add that to row 2 when we create this matrix. So row 1 is unchanged. And now we're going to add, we're going to add these together. So we're going to have 7, 2, and 0. And we added these together to now have to replace row 2 with. Okay, let's perform some elementary row operations. You do need to understand what these symbols mean, okay? So you want to practice that a little bit. Here we're going to replace row 1 with half of row 1. In other words, what are they saying? We're just going to multiply row 1 by 1/2. So if we do that, we will have a -1, 2, and 5, and we're leaving row 2 alone. Now we're going to add row 1 to row 2, and we're going to replace row 2 with that. So row 1 is actually unchanged. So row 1 will stay -1, 2, and 5. And now we're going to add row 1 and row 2 together. And if we do that, if we add these two rows together and put that in as row 2, we will have 0, 7, and 8. Okay. Now what are we going to do? We are going to look at number 7. And in number 7, we are only changing row 2. This is really important. Row 1 and row 3 are going to be untouched. Why don't we just go ahead and write those. Sometimes this helps students to see the unchanged rows first. So we're going to take the opposite of row 3. And what are we going to do with that? We are going to add that to row 2. And doing that, we will have 0, -9, -3, and -18. Okay, finally, the only row that is going to change is row 2 again. So row 1 and row 3 are unchanged. And we're going to now multiply row 2 by a -1/9. So that would be 0, 1, and -3 times a -1/9 is going to give us a +1/3, and a -18 multiplied by a -1/9 is going to give us a +2. Okay, so now let's begin talking about why are we doing this? Why are we learning these row operations? Because here we're going to be using Gaussian elimination and Gauss-Jordan elimination. If we perform repeated row operations, we can actually form an augmented matrix that represents a system of equations that's easier to solve than the original system. In particular, it's easy to solve a system whose augmented matrix is either in row echelon form or the form you're going to really like, reduced row echelon form. So let's talk about row echelon form first. Row echelon form has all rows consisting entirely of zeros at the bottom of the matrix. So any rows that have all zeros, as you can see, are going to be on the bottom. For all other rows, the first non-zero entry is 1, and this is called the leading one. And the leading one is in each non-zero row is to the right of the leading one in the row immediately above. So as you can see, we will have ones on the diagonal, okay? Okay, and both of these are examples of row echelon form. Now let's look at reduced row echelon form. And as you can see, reduced row echelon form is what we saw above with row echelon form. In addition, each row that has a leading entry of 1 has zeros above the leading 1. Okay, so you can see the ones on the diagonal, and now you can see all of these are zeros. Okay, so zeros, and you can see our ones. We don't worry about that row with the all zeros. So after writing an augmented matrix in row echelon form, the corresponding system of linear equations can be solved using back substitution. They are very easy to solve. And this method is called Gaussian elimination. So to solve a system of linear equations using Gaussian elimination, we're going to first write our augmented matrix. That's not too difficult. Then we're going to use elementary row operations that we did practice already, and we are going to write the augmented matrix in row echelon form. And then we'll use back substitution to solve the system, okay? So we are going to begin using Gaussian elimination, and let's go ahead and first write our augmented matrix here. And we have here 3x plus 3 equals 5y plus 4. So that is now 3x minus 5y equals 1. Okay, so now we can go ahead and write this augmented matrix. So we have a 2, a 3, and a 7. And then we have a 3, a -5, and a 1. Now, what we want to do is and I could write these in standard form here. We have 2x plus 3y equals 7, and 3x minus 5y equals 1. So now what we're going to do is we are going to work on making this 2 into a 1. So which one of our operations will allow us to do that? You got it. We are going to multiply row 1 by a half, and that's going to be our new row 1. Okay? And actually, I should probably write that right here. And I think that'll be a little bit easier right above that arrow. Okay? So what did you notice? Row 2 was unchanged, and row 1 is now going to be 1, 3/2, and 7/2. Now, what we're going to work on is we're going to now work on having this 3 become a 0. We need a 0 below that leading 1. So how are we going to do that? Well, we want to use this 1 that we just created and then add that to that row. So what we could do is we could take -3 times row 1, and then we could add that to row 2, and we could replace row 2 with that. So how could we do that? I'll move that over there, make it just a tad bit smaller. And so now what do you notice? Row 1 is not changing. And row 2, we're going to multiply -3 times R1. So that would be -3, -9/2, -21/2. And we're going to add those to row 2. So 3 plus a -3 is a 0. Actually, I could write row 2 here as 3, -5, and 1. And I could show you that we are adding those together. So 0, and that would be -19/2. And then this would be another -19/2. Okay, now we need to work on this -19/2 to become a 1. So I'm going to multiply everything in row 2 by a -2/19 by row 2 and replace row 2 with that. So keep in mind that row 1 stays the same, and row 2, if we multiply by -2/19, we have a 0 and a 1, and we end up with another 1. So as you can see, we have our 1s on the diagonal, and now we could write a system. And this system is x plus 3/2 y equals 7/2, and y is equal to 1. That's what those two, and actually I could write those right here. Y is equal to 1 and x plus 3/2 y is equal to 7/2. So now what could I do? I could use substitution and find what x is equal to. So when y is equal to 1, we're going to have x plus 3/2 times 1 equals 7/2, and x is equal to 2. So the solution to this system is 2, 1. Okay, let's look at number 9. Let's go ahead and get our augmented matrix written. It looks like we have quite a bit of room here. So I might work right below it. And let's go ahead and come up with our augmented matrix. And then what are we going to do here? Well, we want to focus on having this 2 be equal to a 1. So we are going to divide each coefficient in row 1 by 2. So 1/2 row 1 is going to be row 1. That is one of our operations. Actually, why don't we do this? Why don't we replace, because we have a 1 already, why don't we replace row 1 with row 3? Then we're actually using one of our other operations. So as you can see, we have now interchange those 2 rows, and row 2 has been left the same. And I might want to go ahead and just replace row 2 with row 3, and I'll show you why in a minute. So here, row 1 will be 1, I might as well erase this. 1 and 0, and 1, 4, 2, -3. I think that's going to be better. So now that I have this 1 here, now I need to work on getting a 0 here. Coming up with a 0 here. So what could I do? I could multiply row 1 by -1, and replace that, add that to row 2, and replace row 2 with that. Okay? And I could also work on making this a 1. We could do this in the same step. And I could take a -2 times row 1 and add that to row 3 and replace row 3 with that. Now, that seems like a lot, but we are just going to take care of each one of those one by one. As you can see, row 1 is unchanged. We're only replacing row 2 and row 3. Okay, so we're going to take -1 times row 1, and then that would be a -1, a -2, a -1, and a 0, and we're going to add that to row 2. Okay, so we have a 0, a 2, a 1, and a -3. Now we're going to take negative 2 times row 1. I didn't put row 1 there. So negative 2 times row 1. And negative 2 times row 1 is negative 2, negative 4, negative 2, and 0. We're going to add that to row 3. So now we will have 0, negative 10, negative 3, and 7. So we're doing pretty good. We now need to focus on this 2 becoming a 1. Okay. And we could also work on this other 0 first, either way. But we're going to take 1/2 of row 2 and just multiply row 2 by 1/2. How's that sound? Okay. So now we have row 1 remaining the same, row 3 remaining the same, and we're going to take 1/2 of row 2. Okay, so now we are going to work on this negative 10 becoming a 0. So we are going to multiply row 2 by 10 and add that to row 3 and replace row 3 with that. Okay, so row 1 and row 3 are staying the same. Whoops, and row 2 are staying the same. And we're going to take 10 times row 2, which would be 0, 10, 5, and negative 15. And we're going to add that to this row. So 0, 0, 2, and a negative 8. Okay, we're getting there. Now we have to somehow make that 2 become a 1. So what we could do is we could multiply everything in row everything in row 2 by, row 3 by 1/2. So just taking this step by step, you can really just take your time. And dividing by 2, we end up with this matrix. And as you can see, we have 1s on the diagonal. So let's go ahead and write what this system says. We have x plus 2y plus z equals 0. And we have y plus 1/2 z equals a negative 3/2. And then we have z equal to negative 4. So if we have z equal to negative 4, let's go to use z equal to negative 4 in equation 2. So we have y minus 2 equals negative 3/2, and y equals 1/2. So right now we have z equal to -4 and y equal to 1/2. And we could use both of those. So we could use y equal to 1/2. I can do that over here. Y equal to 1/2 and z equal to -4 in equation 1. So we could have x, see if I can move all of this up just a bit. So we have x plus 1/2 times 2y is just y. Whoops. Y is 1/2. So that would be a 1 plus z equals 0. So as you can see, x would be equal to 3. So the solution here is 3, 1/2, -4. Okay, well, what if we would now want to have a reduced row echelon form? So this is called the Gauss-Jordan elimination method. We are actually going to continue to perform operations on matrix in number 9, on the matrix in number 9. And we're going to do that until it is in reduced row echelon form. Then we're going to determine the solution simply by inspection. So no substitution will be needed. Okay, so looking at where we were in number 9, as you can see this matrix right here. Okay, so let's go ahead and write that matrix. So we have 1, 2, 1, 0, 1, 1/2, -3/2, and 0, 0, 1, -4. Okay, so we will work on this value right here, and we will want that to be a 0. So we will take -2 times row 2, and we will add that to row 1 and replace row 1 with that. Okay, so let's go ahead and do that. So the only row that's changing is row 1. So -2 times row 2 would be 0, -2, -1, and a 3. And we're adding that to row 1. So there we would have 1, which we already had, 0, there's that 0, 0, and 3. Okay, so now we want to focus on this 1/2. So how we would have that 1/2 become a 0 is to multiply row 2 by a -1/2. Excuse me, row 3 by a -1/2, and add that to row 2 and replace row 2 with that. Okay, so let's see what we have now. The only row that's changing is 2. And we're going to take negative 1/2 of row 3. So that's 0, 0, negative 1/2, and a 2. And we're going to add that to row 2, which is a 0, 1, 1/2, negative 3/2. So we're going to add that. And that's going to come out to 0, 1, 0. And then we're going to have 1/2. And now, as you can see, we have ones on the diagonals. We have our zeros in all of the other entries. And now, without any work, we can write our solutions. X equals to 3, y equal to 1/2, and z equal to negative 4. And as you can see, that's exactly what we had here, but we used substitution. Okay, let's try one more before we solve an applications problem. So I'm just going to go ahead and jump right in to writing my augmented matrix. Okay, our focus, we already have this 1 here already. So now we want to go ahead and focus on both of these values being 0. And how we would do that is we could take negative 2 times row 1 and add that to row 2 and replace row 2 with that. And then negative 5 times row 1 and add that to row 3 and replace row 3 with this. So it's probably getting a little bit easier. You can see how you can use these ones. Row 1 is the only row not changing. And I could probably bring this down just a touch. And I could make that just a tad bit smaller. Okay. So now, if we're going to take negative 2 times row 1, and we're going to add that to row 2, we will have 0, 15, negative 15, and negative 15. And then negative 5 times row 1 would be negative 5, 30, negative 40, and a negative 28. And I'm going to add that to row 3. And as you can see, I will have 0, 39, negative 57, and negative 32. Okay, so whoops, negative 39. I think this should have been a negative 35, yes. So then this is a negative 39. Okay, so now what's our focus? We need to have this 15 as a 1. Okay, so how will we do that? Well, we could go ahead and multiply each term by 1/15. Each coefficient, so 1/15 times row 2, and we'll replace row 2 with that. So row 1 and row 3 are unchanged. Okay. So now what are we going to do? Well, our focus now is to have this 39 as a 0. So we could multiply row 2, use that 1 that we just got, multiply row 2 by negative 39 and add that to row 3 and replace row 3 with that. So row 1 and row 2 are unchanged. Okay, so now if we have negative 39 times row 2, you'll see we have a 0 and a 0, and a negative 39 times a negative 1 is a positive 39, plus a negative 57 will give us a negative 18, and we will have 0 here. Okay, so now our next focus will be, for this negative 18 to become a 1. And we'll just divide all of those terms by negative 18, and it's only going to change that one entry. So we will have negative 1/18 times row 3 and replace row 3. So there's row 1, and there is row 2. And now we're just going to divide everything by a negative 18. And there we have it. So now our focus is going to be coming up with a 0 in these 3 entries right here. 1, 2, and 3. So what we could do here is we could at least work on a couple. Let's go ahead and take this one off, and we can work on that negative 6 in a minute. So we'll just do 2 different things. We'll first add row 3 and row 2 together, and that will give us what we need in row 2. So we will have row 2 plus row 3, and that will replace row 2, and that will help us with this negative 1. Then we could take a negative 8 and multiply it by row 3. Add that to row 1, and that will then replace row 1 and help us with that 8. Okay, so as you can see, row 3 is going to be unchanged. And row 2, we're just going to add row 2 and row 3 together. So that, and we're going to replace row 2 with it. So that's a 0, a 1, a 0, and a negative 1. Okay? And now row 1, we're going to take negative 8 times row 3, and we're going to add that to row 1. And so we're going to have a 1, a negative 6, and this is going to give us our 0. And then, of course, you can see we will have a 7. Okay. So finally, we just have this negative 6 that we need to work on. And that's not too difficult. All we have to do is multiply row 2 by 6 and add that to row 1. And then we'll replace row 1 with that. So row 2 and row 3 are unchanged, and 6 times row 2 added to row 1, as you can see, we'll have a 1, 0, 0, and a 1. So now, as you can see, x is equal to 1, y is equal to -1, and z is equal to 0. I wonder if I could make this a little bit narrower. Just trying to bring it in a bit so that I could put these to the right like that. So this solution is 1, -1, 0. Okay, let's try an applications problem, and then we will wrap this unit, this section up. The University of Texas at Austin has 3 times as many students enrolled as the University of Miami. University of California, Berkeley has 3,000 more than twice the number of students at Miami. If 3 schools have a total enrollment of 96,000 students, what is the enrollment at each school? Well, the most important thing is to go ahead and define your variables. So why don't we go ahead and let X be students at Texas and Y be students at Miami. That would be the number of students. And then Z, the number of students at Berkeley. And so the system that we have, 3 times as many enrolled as Miami. So what could we say? We could say that X was equal to 3Y. Then 3,000 more than twice the number of students. We could say that Z, the number at Berkeley, is 3,000 plus 2Y. And finally, all of the students added together equal 96,000. So, simplifying that, we have X minus 3Y is equal to 0. We have negative 2Y plus Z equals 3,000. And then, of course, we have our X plus Y plus Z equals 96,000. So let's begin with our augmented matrix. And that would be 1, -3, 0. And then a 0. And then 0, -2, 1, 3,000. And 1, 1, 1, 96,000. So our first focus is going to be on this 1, okay? So let's go ahead and take care of that. And what we'll have to do is, all we have to do is take the opposite of row 1 and add it to 3, and we'll replace 3 with that. So row 1 and row 2 are unchanged. And now we're going to take the opposite of row 1 and add it to row 2. And there you have it. So now our next focus is going to be this 4. So we would like that to also be a 0. So we could go ahead and take 2 times row 2, add it to row 3, and replace row 3 with that. So row 1 and row 2 are unchanged. And so twice row 2, adding that would give us 102,000. Okay, So our next focus would be, and you can work around any way you'd like. I would think we could go ahead and work on this 3. So why don't we divide row 3 or multiply row 3 by 1/3. So we have 0, 0, 1, and then of course 102,000 divided by 3 is 34,000. Okay, so now what we can do is we could focus on this 1, and we could replace that with a 0. You can work in any order that you'd like. So what we're going to do now is we're going to take the opposite of row 3, add it to row 2, and that's what our new row 2 is going to be. So row 1 is unchanged, and row 3 is unchanged. And then the opposite of row 3, adding, we will have a 0, a -2, a 0, and now we will have negative 31,000. Okay, so our next focus is going to be on row 2, and we could work on this -2. And we'll just divide or multiply row 2 by a -1/2. And so here we will have 0, 1, 0, and we will have 15,500, and that's positive because that was a -1/2. Okay, so now what we could focus on would be this -3, and after that we should be able to see our solution. So we're going to take 3 times row 2, add that to row 1, and that will be our new row 1. So row 2 and row 3 are unchanged. And if we take 3 times row 2 and add it to row 1, we still have our 1, and now we have our 0, and we still have that 0 there, and then we will have 46,500 because 3 times row 2 is that. So what do you notice? We have 1s on the diagonal. So we have our reduced row echelon form, and we now can say that x is equal to 46,500, y is equal to 15,500, and z is equal to 34,000. And each of those, you can see the number of students at each university. And that concludes this section.